ME204, Equation of Motion for Rigid Bodies, Slipping versus Tipping. Sometimes there are some special cases that we need to consider when we're dealing with force equals mass times acceleration. In this case, we've got a situation where we've got to decide whether a box is going to slip or whether it's going to tip. There are two cases that we have to consider. In the first case, we have static friction that is exceeded and the box begins to slide. Kinetic friction takes over, and the resultant normal force occurs somewhere between the center of mass and the corner of the box. In case 2, the static friction is not overcome. However, the moment is sufficient to cause the normal force to shift to the corner of the box, and the box begins to rotate about the corner. So how do we decide which case we're dealing with, and how do we solve these types of problems? Let's look at some common steps that we can take to be able to solve this type of a problem. The first thing that we want to do is check for a static solution. So we're going to write our equations, summing the forces in the x and in the y, and the moments about the center of gravity, and set them equal to 0. If we sum forces in the y direction and set it equal to 0, we can find what the normal force is, n. If we sum forces in the x direction and set it equal to 0, we can find what the friction force is, F sub s. Then we can check that friction force to see if it exceeds the maximum static friction, our coefficient of static friction times the normal force. If F sub s is greater than mu sub s times n, then the problem is dynamic and it's going to either slip or tip. Now we have to decide which case it's going to be. Is it going to slip or is it going to tip? So we sum moments about the center of gravity, setting it equal to 0, and we find the location of the normal force from the center of mass, or from the center of gravity. We'll call that position x as it is drawn on our free body diagram. If x is greater than the width of the box, or half the width of the box, d, then the problem is dynamic and it's going to tip. And we'll use steps 2 and 4 that we'll show in a minute to solve that problem. If x is less than half the width of the box, or less than or equal to d, and our friction is greater than mu sub s times n, then the problem is dynamic and the box is going to slip, and we'll use steps 2 and 3. So what are steps 2 and 3? Well, step 2 is to go ahead and draw our free body and kinetic diagrams and write the dynamic equations. We've already got a free body diagram. Our kinetic diagram may look something like this. If the box is going to slip, then we will for sure have our mass times acceleration in the x direction. If the box tips, then we may have some acceleration in the y direction, as well as a rotation, alpha. Now we can write our equation, summing forces in the x direction and setting it equal to mass times acceleration in the x direction. Sum our forces in the y direction and set it equal to mass times acceleration in the y direction. And summing the moments about the center of gravity and setting that equal to our mass moment of inertia times the angular acceleration. If it's the slip condition, then we know there's no acceleration in the y direction and there's no rotation. We also know that if it's slipping, the friction will be exactly our coefficient of kinetic friction times the normal force, mu sub k times n. With these known conditions, we can go ahead and solve our dynamic equations. If it's the tip condition, then our tangential acceleration is equal to our angular acceleration times the radius, and our radius would be the point where the object is rotating about, or the corner of the box, to the center of gravity. We would also know that the normal force acts at the corner of the box, at the position D as drawn on our free body diagram. Then we can solve the dynamic equations for the unknowns. To help illustrate these steps a little bit better, let's take a look at an example. In this example, we've got a box that's 50 kilograms. It has a force of 260 newtons that's applied 1.5 meters from the ground up the side of the box. The box is 2 meters by 2 meters, and the coefficient of static friction is 0.5, the coefficient of kinetic friction is 0.3, and the radius of gyration is 0.82 meters. We want to find out if the box is going to slip, tip, or stay static. If it slips or tips, let's determine what the acceleration of the block is. First thing that we want to do is solve this statically. So we'll draw our free body diagram. We'll have a weight, 50 times 9.81, which will give us 490.5 newtons. We'll have the applied force of 260 newtons. We'll have a normal force, N, and we'll have some friction force that we don't know at this point, so we'll just label it F sub s. And we would note that the normal force could act at some position x away from the center of gravity. If we sum forces in the x direction, then we've got 260 newtons, the applied force, minus the friction equals 0. So our friction would have to equal 260 newtons in order for this to be a static problem. We then sum forces in the y direction. Our normal force minus our weight, 490.5 newtons, is equal to 0. So our normal force would be 490.5 newtons. Our maximum static friction would be our coefficient of static friction times the normal force, or 0.5 times 490.5, which would give us 245.25 newtons. Now, the friction that we calculated, 260 newtons, is greater than our 245.25 newtons, meaning the friction we calculated is greater than our maximum static friction. Therefore, our problem is dynamic. So we need to check the tip condition. We sum moments about the center of gravity. So our applied force of 260 newtons times its moment arm from the center of gravity, which would be 0.5 meters, not the 1.5, because we're not summing about the bottom, we're summing about the center of mass. So 260 times 0.5 meters plus our maximum static friction, mu sub s times n, times 1. We use our maximum static friction in this case because we want to find the location of the normal force when we reach that point. So we have our maximum static friction times 1 minus our normal force times the position x. We know what the normal force is. We've already calculated that to be 490.5. If we substitute that into our equation and then solve for x, we find that x is equal to 0.77 meters, which is less than 1 meter, which is half the width of the block. Therefore, the block is going to slip before it tips. It will exceed the maximum static friction before the normal force moves to the corner of the box. Now, knowing that we're in the slip condition, we can solve it dynamically. Here's our free body diagram, like we had before. Now we have a kinetic diagram that only includes our acceleration in the x direction. Writing our equations, sum of the forces in the x direction equal mass times acceleration in the x direction. Sum of the forces in the y direction will equal 0 since our acceleration in the y direction is 0. And using the equation, sum of the moments about the center of gravity equals the mass moment of inertia about the center of gravity times our angular acceleration, which is also 0. We can solve in the slip condition. In this case, sum of the forces in the x direction is 260, our applied force, minus our friction force, will be equal to our mass, 50 kilograms, times the acceleration in the x direction. However, we know exactly what the friction is going to be. It will be equal to our kinetic friction, or our coefficient of kinetic friction times the normal force. Summing the forces in the y direction, we get our normal force minus 490.5 is equal to 0, so our normal force is still equal to 490.5 newtons. And substituting that into our friction, we get that our coefficient of kinetic friction, 0.3, times our normal force is equal to 147.15 newtons. Substituting that into our equation for the forces in the x direction, we get 260 minus 147.15 is equal to our mass, 50 kilograms, times our acceleration in the x direction. And solving for our acceleration in the x direction, we get that it's accelerating at 2.26 meters per second squared, and it is in fact slipping. Our next topic is equation of motion for translating rigid bodies, rolling versus sliding.